Most people moving and working in the vertical world need it, a rope. But interestingly, it is pretty useless without one thing, some kind of end termination. In this series, we take a closer look at these terminations and in this episode specifically at splices and what their limitations really are. Hi, my name is Phil from the Iterate Knowledge Base. Splices are just looking beautiful, but it can be a little bit of an intimidating thought that you don't see what is going on inside, right? In the last episode, we talked about different types of splices. In this episode, we want to learn more about risks and limitations that those different types might bear in real-world scenarios and examine them. For this video, we came up with 3 tests out of our own risk assessment for splices. So if you have more ideas about things you would like to see in the future to be tested, just write them in the comment section. To start with, let's take a look at the coreless splices again. We already mentioned here that these kind of splices require that the sheath is strong enough to reach a value above 15 kN in a loop if we are talking about static ropes according to EN 1891 type A. So let's take a look at the scenario where a considerable amount of the sheath yarns get seriously damaged. Something that we could definitely imagine in a real-world scenario, right? For this test, we use a coreless ice splice on a certain rope with a measured strength of 18 kN on this splice. We then test 2 scenarios. For one test, we cut half of the sheath strands on the outside of the eye, and for the second test, we cut half of the sheath strands on the inside of the eye. And now let's simply pull them. Interestingly, in this case, we see that the resulting strength still lies slightly above the 15 kN. For the next scenario, we look at cyclical loads. So think of someone ascending a rope that is attached at its splice. And here we examine the 2 present basic splicing construction: wedged splices for such ropes with inner core strands and interlocked splices for double braid constructions. Have a look at the previous episodes to get the detailed explanation again. The concern here is that especially wedged constructions could come easily undone, as when the 2 elements wedged together would wiggle apart from each other, the splice would just open up. Interlocked splices, however, in theory should not bear this risk too much, as we saw in the last episode that they form a continuous loop forming the eye. So the eye could get bigger in size, but it should never open up. So let's have a look. We put both splice constructions on our cycle machine. It continuously loads the splices with 150 kilos in that case, and what happens is just what was foreseeable. The wedged construction eventually opens up completely. The interlocked splice eye gets a little bigger, but never gives up. This is the #1 reason why splices should always be secured. In splicing vocabulary, this is often referred to as whipping, and there are different ways of achieving this. A whip is not load-bearing, it doesn't add anything to the maximum breaking strength of the splice. What it does is that it guarantees that all splice elements just stay in their place, being able to develop their necessary forces that make the splice hold what it's supposed to. And we see that when we repeat the test with the wedged splice that is properly secured, the splice does not open up at all. Generally, from a manufacturing point of view, we would advise to always secure any splices. But interlocking splices are certainly much more robust to the risk of coming undone by a cyclic load. Finally, for this video, we look at cross-loading scenarios. A typical real-world misuse and certainly a risk. For this test, we cross-load a figure of 8, a sewn termination, an interlocked coreless eye splice, as well as a wedged coreless eye splice. And we cross-load each of these rope terminations in an axial direction parallel to the rope, as well as a radial direction, just to see if that makes any difference. Again, let's see what happens. Surprisingly, the knot by far is the most robust termination in this regard, and another argument for this kind of termination. The sewn termination, cross-loaded, gets to over 7 kN in this case, and then of course fails completely. The interlocked splice might not reach the strength value of a knot when cross-loaded, but it happens what we already assumed for the cyclic loads. The loop just gets pulled out and gets bigger and bigger, at a very similar strength value as the sewn termination, but the big difference here is that it does not fail. Eventually it will of course fail, either because the whole core is pulled out or the sheath gets so bulged up that no core can be pulled out anymore. But we could not achieve this on this testing setup. The worst construction here is the wedged splice. Even a properly whipped splice is easily pulled out at a very low force. So this scenario is definitely a serious risk to consider for practice use for these kind of splices. Here you got all the cross-loading results again summed up. Interestingly, cross-loading a termination in these cases in different directions makes a little difference, as you can see, but nothing very significant. In summary, it can be said that especially interlocked splices are quite robust constructions, and that certain attention and awareness is needed on the other hand for wedged splices.